This is AP Precalculus. We are on notes, topic 2.5 for exponential function, context, and data modeling. All right, so bear with me as I read along. Sometimes data from an exponential function does not display a proportional growth pattern. This is due to a vertical translation of the function. However, if we can add or subtract constant from the output values to reveal a proportional growth pattern, then the initial fraction was also exponential. So, in the following problems, we have some table values and we need to figure out an equation and we need to add or subtract values. While it might be fun to just try to add and subtract right off the bat, sometimes it doesn't work. So I'm going to go ahead and kind of brute force this. And here's the way that I'm going to do this. I'm going to say, okay, I'm going to do the first difference first. And to get from 7 to 13, I'm adding 6. From 13 to 25, I'm adding 12. 25 to 49, that's 24. And 49 to 97, that's 48. So you can notice here that the first differences are constantly multiplying by 2, multiplying by 2, multiplying by 2, which means I'm kind of, I have a clue in terms of what my equation is going to be. I'm going to have some sort of f of x where I have some initial number. Well, you might want to say, oh, that initial number, whenever the value is 0, it's 7. We have to change that 7 to something. But we do know what that common ratio is going to be. The common ratio is going to be 2 to the power of x. And then because these functions have been shifted up and down, there's a vertical shift, we're also going to have a number out here. I know that this number plus this number has to add up to 7 as a clue. I need to figure out how am I going to constantly make sure that I'm multiplying by 2 at each of these steps. So I'm going to go ahead and erase this word now. I'm going to say, okay, how could I do something? Well, let's try adding 1. If I add 1 to it, that's going to be 8 to 14. Notice I'm adding 1 to 7, adding 1 to 13. 8 to 14, that's not multiplying by 2. So that was not working. If I go up to 9 and then 15, still not multiplying by 2. I think I'm going farther away. Maybe I should try subtracting 1. So if I go here and I say, okay, what happens if I do subtract 1? If I subtract 1, then I'm going to be doing 6 to 12. And check it out. Okay, so 6 to 12, that is multiplying by 2. So all of these must be subtracting 1. Let's just double check that. If I subtract 1, 24, subtract 1, 48, subtract 1, 96. Okay, each of these is multiplying by 2 at each step. So that's the pattern that I want here. So really, I'm trying to subtract 1. So subtract 1 is the vertical shift that I have, which means my number should have started at a 6. So I'm going to have my 6 for my initial term here. All right, so I have my equation. I'm not going to rewrite it out, but it does look like this. All right, in part B, again, I want to figure out what that ratio is to multiply by. So I'm going to look at the first differences first. So I'm going to say the first differences, to get from 2 to 10, I'm doing plus 8. From 10 to 34, I'm doing plus 24. From 34 to 106, that's 72, I think. And that's going to be, it's 218, it looks like. Okay, so what am I multiplying by at each step? To get from here to here, I'm multiplying by 3. Is that multiplying? That's multiplying by 3. Okay, all of these are multiplied by 3. So I know that my g of x function is going to have some sort of initial number here times my common ratio here is 3 to the power of x, and then I'm going to add some sort of number off to the side. So all of this work was just to figure out what that common ratio is. Now what I need to do is figure out what sort of vertical shift I have. So for my vertical shift, let's try subtracting 1 again. If I subtract 1, I'm going to get 1 and 9. Okay, that went farther away. 2 to 10 was multiplying by 5. 1 and 9 is multiplying by 9. I'm going the wrong direction. So instead of subtracting 1, let me try to add 1, see what happens. So if I add 1 to this, I'm going to have 3 goes to 11. Okay, that doesn't make sense because I can't get anything to 11. It's a prime number. Let's try adding 2. So if I add 2 here, I'm going to get 4 to 12. Okay, check this out. 4 to 12, this is working because this is multiplied by 3. 4 to 12, yeah, so times 3. Let's say that's times 3. And then let's see, keep adding 2. That's going to be 36. That's still multiplying by 3. Okay, we found it. It's just plus 2. So it's going to be 108 and 3, 24. Each of these is multiplied by 3. Okay, so the original number should have been 4. So I'm going to come down here and say the original number should have been 4. And to get that, I had to add 2. And again, these two numbers, 4 plus 2, should add up to that original number. That's not correct, is it? That's I misspoke here. Really what we have here is this number goes here, and what do we need to do to get to that number? We needed to subtract. No, this should have been adding 1. I apologize. These two numbers should add up, so I need to come back here and say, okay, this needs to change into a plus 1. If I add 1 to this, I'm speaking out loud here. So 6 plus 1 adds up to 7. They need to be these values here. So this plus 2 doesn't make any sense. I need to say, okay, I start at 4 and then I have to somehow get to 2, which means I have to subtract 2 here. Let's come in here and say this is a minus 2. Minus 2. Whoa, minus 2. Bad 2. Okay, this now makes sense because just plug it in 0. If I plug in 0, I should have an output of 2, right? If I plug in 0, 3 to the power of 0 is 1. 1 times 4 is 4. 4 minus 2 is 2. Okay, that seems to be working well. So it's kind of like the opposite of what I'm doing up here, it looks like. All right, over here, what do we have happening? I can already see that number is really close to 64. That number is close to 2. I think I really just need to, or that's close to 4, I guess. I can really just add 1. I'm going to try that right now and see what happens. Okay, so I'm going to go ahead and say plus 1. That's going to be 64, goes into 32, goes into 16. And you can see, okay, each of these are dividing by 2. That's 8, and that's 4. Each of these, to get from here to here, we're multiplying by a half, multiplying by a half, etc., etc. Which means my h of x function here is going to be equal to, my initial number should have been 64. And then my common ratio is a half. And that's the power of x, and then to get from 64 to 63, I have to subtract 1. Excellent. All right, so modeling exponential functions from data. So an exponential function can be constructed if we are given one of these two things. We can either be given the common ratio and the initial value, which again are 2 input pairs, or just other 2 random input pairs. It doesn't really matter. So the initial value is a value. The common ratio gives you the idea of how to get to the next step. This is just 2 different points. Either way, we can find an equation. All right, so let's try an example. This one is going to need a calculator. So let me go ahead and pull up my calculator. Let's go over here to my calculator. All right, so according to this, let me go ahead and read the problem. Between 0 and 30 minutes, the number of fans inside a large sports stadium can be modeled by an exponential function where f is the number of fans inside the stadium at t minutes after the door is open. There are 47 people at 2 minutes. Okay, I'm going to underline that. I think that's going to be important. We'll come back to that. But there's 47 people in the stadium at 2 minutes, and there's 2,602 fans at 20 minutes. Use the data to write 2 equations that can be used to find the values of the constants a and b for the expression. So it doesn't even want us to find the equation, just wants us to write the equations, very similar to the test from the last unit. So the first equation here, again, I'm essentially rewriting this equation down here, but I'm filling in anything that we know. We know f of the time, f of 2, is equal to, I don't know what the initial value is in the equation. I don't know what that common base is. The calculator will find values of a and b for me. And you can see it over here. It'll give me values of a and give me values of b, but I don't know what those are. And then I do know the time up here. This time and this time are the same. So I can say this time are the same, and that's 2. And really what I should say here is f of 2 is a value. Let me go ahead and I can erase this, or if you're just following me along with the notes, you can say that that's equal to the actual number. The number here is 47. So that's the first equation. The next equation is going to be really similar to this. This is 2,602 fans is equal to a times b to the power of how many minutes? 20 minutes. So both of those equations will help me to derive the actual equation. And then we're going to actually use a calculator for that. And you can see what they're doing in their table over here. They plugged in 247, and they plugged in 20 and 2,602, 20, 2,602. And then here are the steps. You enter the data, you go to the calculation of that data, and you go to the exponential regression, and then you just put in the equation, make sure you're storing it into y1, and then it will spit out the values. And the values for this one is kind of interesting. So that the common ratio for the problem that we were just given was 1.25, if I'm rounding to 3 decimal places. And then the initial value is 30, which means when they first started, there are 30 people inside. And it's increasing by about 30%. Okay, so that's how you create it. In the next problem, we're actually going to use the calculator here. So here's an equation, or here's a table. We need to find, first write the 2 equations that can be used, just like we did in the last problem, and then actually use the calculator to find those values of a and b. Okay, so the first equation, again, we have to memorize the general form of an exponential equation. The general form is, hey, do the output first, 21.54, and that's going to be equal to a times b to the power of 3 in this case. And then the next equation is going to be 3.62, and that's going to be equal to a times b to the power of its input, which is going to be 8. All right, we have our equations entered. Let's go ahead and enter it into our calculator. So I'm going to go to my stat edit, and I'm going to enter in the equations in here. Let me go ahead and clear out of everything here. I want to clear, enter, go over here and clear everything, enter. Oop. I went too many times. Clear, enter. Okay, so we have blank lists, and I'm going to enter 3 and 8 for my inputs. And for my outputs, I'm going to do 21.54, enter, and 3.62. Okay, I have my data entered. Now I'm going to go to the stat button again, and I'm going to go to the right to the calculation tab, and I'm going to go down to the exponential regression, or I can just hit 0. And it already has the list for me. I need to come up here and store the equation in y1. So where it says store equation, I'm going to hit alpha trace and hit y1, and then hit enter to calculate. Okay, so it is telling me my values of a. My value for a is 62, always round to 3 decimal places, so 0.801. And my value for b here is going to be 0.699999, but if I'm rounding to 3 decimal places, that's 0.700 to 3 decimal places. All right, nice. So it's time to talk about the natural base, e. So e is 2.718 roughly. Again, if you're trying to memorize digits of e because you're trying to do some sort of cool competition, you want to remember it's 2.7 and then 18, 28, that's Andrew Jackson, and then another 18, 28, another Andrew Jackson, the year that he was elected president. And then when Andrew Jackson was 90 years old, he carried a 45 on each hip, so you'll have 45 on that hip and a 45 on that hip, and you've memorized, what is that, like a bunch of digits of e. But again, you just need to memorize about 2.7-ish. And it's used generically when you have contextual scenarios where you actually have real life scenarios. So bacteria culture, right? It is modeled by this equation, and t is every hour. Okay, so we know it's going to be modeled by an exponential because it gives us a general form of an exponential in part A, and we need to find a value of b. What is an equivalent expression for this b? So in here, I'm going to rewrite this as just same thing as our last unit. A has not changed anything. It's still 17. So I'm rewriting this a of t now. Is still 17. I'm rewriting this expression up here, but I'm going to rewrite this so this is a new base. I'm going to say that this is times e to the power of 0.31, and this entire thing to the power of t, because when I have a power to a power, I multiply it and I get 0.31 t. And I can rewrite this base now using my calculator. I can clear out of this, and I can say what is e, so that is the second natural log button, so second ln, so it's e to the power of 0.31, and that looks like it's the new base is 1.363. This is going to be equal to 1. I need to have that number out front, don't I? So it's still 17 times our new base, which is 1.363, 1.363 to the power of t, which means our new base here, I guess what it really wanted, our new base is supposed to be 1.363. Excellent. Okay, what is part B saying? Find the average rate of change of that capital B function from 1 to 7. Oh, and by the way, I think you might, I'm not sure if this year I print out find A. A never changes. A is always 17. So if your notes say find A will be 17. B is the one that you have to change, which is the properties of exponents, but A will always be 17 no matter what. All right, so find the average rate of change over 1 to 7. Okay, so this is just average rate of change. You want to cross this off. Every single time you see it, average rate of change, you want to change this to the word slope. Find the slope over that interval. So between 1 and 7, that's going to be b of 7 minus b of 1. Just from 1 to 7. Yeah, 1 to 7. All over 7 minus 1. Over and over, it's the same slope formula where it's the y coordinates divided by the input, the x coordinates. So b of 7, I don't know what that is, but I'm going to go ahead and plug it in. So I'm going to go to my y equals button. Let's clear out of that. I'm going to type in 17 and then e, which is second ln, e to the power of 0.31t. So 0.31, and then I have to enter in an x. Okay, so I have my function entered. So if I hit second mode to quit out of this, I can now do b of 7 by doing alpha trace. So you do my y1, hit y1, and then start your parentheses of 7. And when I type that in, I get, write this down, 148.7 891 if I'm rounding. 891 minus, okay, I need to enter this next one in, so it's going to be alpha trace y1, start the parentheses, y1 of 1, and hit enter. And that's going to be 23.178. 23.178. And that's all divided by 7 minus 1 is 6. Okay, I just need to calculate what these two things are. So I'm going to do this perfectly. I'm going to do y1 of 7 minus vars, or it's going to be alpha trace y1 of 1 and the parentheses. Oh, I accidentally hit 9. And the parentheses. Okay, so I did the subtraction problem perfectly. The answer is stored. I'm just going to hit divided by 6. And I have never rounded my answer until just right now, in terms of the calculator right now. This is equal to 20.952. Excellent. All right, so that's the slope. And then finally, find the number of bacteria predicted after 15 hours. So that's easy to do. Let's just plug in 15 into our function. So I can do that pretty easily. I do alpha trace y1. Oh, I need to get out of this, don't I? Second mode to quit out of this. So alpha trace, there we go, y1 of 15. y1 of 15. And I get, wow, 1,777.945. And usually bacteria is like a count number, so it's rounded to whole numbers. Round to the nearest whole number, this is going to be 1,778 bacteria. All right, and I think this is our last example for the notes because then it moves on to the worksheet. Yes, indeed. So after 50 deer were introduced to a large wooded area, the population of deer in the wooded area can be modeled by an exponential equation. Perfect. The population increases by 13%. Okay, so the two pieces that I'm looking at, it tells us it increased by 13% and there were originally 50 deer. So I need to find the values of A and B, and then I'm going to write an expression for our new exponential equation. So the first thing that I know is that A is always the initial amount. So A in this case is equal to 50. It says that there's originally 50 deer. And B is going to be a little bit tricky, but if you remember all the way back from Algebra 2, the way that we do percentages is you turn it into a rate by doing this. You say it's 1, you can either do plus or minus the rate as a decimal, and that is the new percent. So in this case, we are increasing, so that means I'm going to be adding. This is going to be 1 plus our rate, which is 13%. As a decimal, that is 0.13, because again, you move the decimal 1, 2 to the left. It's kind of hard to see there with the underlining, but again, every time that you have a percent, move the decimal 1, 2 to the left, and we'll always get into the decimal. Okay, so this is 1.13 for my B, and then therefore my exponential equation is going to be capital D of T is originally 50 deer times 1.13, and this is going to be to the power of T. So we've got our equation. Okay, what does this say? According to the model that we just found, what is the population of the deer after 6 years? So we just need to plug this in. So I'm just going to rewrite this. This is going to be D of, we're plugging in 6. So we'll say capital D of 6, and this is going to be equal to, just rewriting our equation, 50 times 1.13, it was 1.13, yep, to the power of 6. And I just need to type that into the calculator. So this is going to be 50 times 1.13 to the power of 6. So the power key is our little caret above the division key, and then we type in 6 and hit enter. What do we get? We have about 104.098. 098. Because deer, you can't have 0.098 of a deer, we'll round that to the nearest whole number and we'll say that is approximately 104 deer. All right, finally, find an equivalent expression where T is measured in years instead of months. Okay, so we're going to take our same equation. So we're going to say D of 6, or not D of 6, D of T, and that's going to be equal to, we never change that first number. It's still 50. Our initial number is still 50. This is the thing that's going to have to change. It's 1.13. Our T has to change. So let me ask you guys a question. If I was measuring, I was originally measuring it in years, I guess. Does it say years? T represents the number of years. Now it's going to represent months, which means I need to convert months to year. So originally, I'm going to say my expression is T. I'm going to do it up here. My expression is T, which is in months. Or sorry, T was in years. Sorry. T was in years. And I need to convert it to months. So if I'm converting it to months, I'm multiplying by 12 and I'm going to get months, right? Now this needs to be the input. So I need to divide this number by 12 in order to get it to the number of years. So if I say, I'm trying to get years by itself because originally I still have t, I'm going to say if I divide both sides by 12, I essentially have months divided by 12. This is now t divided by 12. I know that it made sense in my head, but when I said it out loud, I feel like I lost some students. Picture this. If I put 12 in here, that means I'm doing 12 months, which means this entire power is 1, just like it used to be. Up here, the 6 represented years. So in order to make sure that this is still in years, I need to divide by 12. So for example, if I did 6 months, that would be 6 over 12, which is a half. I'm doing half of a year. Whatever you do up here, make sure that it feels like it is in the original unit. This still feels like it's in years, because if I enter in a 12 here, this is still in years up here. I just had to divide by 12 to convert from months to years. That's my best way of explaining it, but I think I can do it better in person if I can talk to you guys later. So that does conclude our lesson for topic 2.5 for AP Precalculus on exponential function, context, and data modeling. Thanks for watching.